Good afternoon. Welcome to Knowledge Hub by Sri Chaitanya. I, Harish Sen, Senior Physics Faculty. Welcome back to you another lecture of physics. We will continue with the units and measurements chapter. This is our third day, or I think a second day for this chapter. So let's start without any further ado. So today we are going to study about dimensions. In the first lecture, we studied about units, what units are, what physical quantities are, and how they are important. So today we are going to study about dimensions. And so what are dimensions basically? So if you know units, dimensions are very simple. So first of all, we in the last class we studied about 7 fundamental quantities, right? 7 fundamental units. And the 7 fundamental quantities were, so let's look at the 7 fundamental quantities. They were length, mass, time, temperature, amount of substance, electric current and luminous intensity. These were my 7 fundamental quantities. So if I want to write my 7 fundamental quantities, what will I write? The units, if I want to write for the 7 fundamental quantities, the units for length is meters, yes, mass is kgs, for time is seconds. Now for temperature, I measure temperature in Kelvin. Amount of substance is mole. Electric current is ampere. And luminous intensity is candela. So these were the units of my 7 fundamental quantities. So now what dimensions are? So let's look at the definition. Dimensions are the power to which the base quantities are raised in order to represent that quantity. So now we have some terms here. So powers to which the base quantities are raised. Yes, so what is power and what is my base quantity? So what is base quantity here and what is power? So my base quantity will be my 7 fundamental quantities. And what do you mean by a power? So if I say x power 2, that means x raised to 2. If I say y cube, then the power is 3. So power here will be the power to which the fundamental quantity is raised. So let's look that with an example. So meter. So the dimension formula for that is length, right? Meter is basically length, L. So L raised to 1. Now if there was meter square here, I would have written L, that is for meter I will write L, and square, for square I will raise to 2. So this L is my base quantity, this one is my power. For kg I will write m, because mass I represent as m. This is the dimensional formula for m raised to 1. Second is time is represented as t and t raised to 1. Kelvin is K raised to 1. Mole, I will write mole raised to 1. Ampere is A raised to 1. And this is CD raised to 1. So if you look closely here, for our 7 fundamental quantities, the power is 1. Yes, and these are the base fundamental quantities. Yes, so we have to remember my 7 fundamental quantities, the units and their dimensions. Using this, we will be able to write the dimension or the units for any of the other derived fundamental or physical quantities. So let's write. So let's see. So now I have area here. Yes. So let's first write the dimension. To write the dimension, of any physical quantity I will be required to write a formula for that physical quantity. So what is the first thing? First thing, I will have to write the formula for that physical quantity for which I have to find the dimensions. My second step, using the formula, I will write the units of the quantity in terms of seven fundamental, that is 7, that is fundamental. Okay, so these are the two steps. So first we write the formula of the physical quantity for which we have to find the dimensional formula, the dimensions, and then we write the units in terms of the 7 fundamental quantities. So these are the main two steps which we require. So let's try to find the dimensional formula for this physical quantity, and that physical quantity is area. So for area, what is the formula you can remember? So for area, I remember the formula is pi r square. Okay. So as you say area, I remember this formula, pi r square. So if I remember pi r square, this one, pi r square. So if you look closely here, so area is equal to pi into r square, right? Radius square. Now I can say the dimension for A is equal to dimension of pi, okay, into dimension of r square. Or my second step, so this is basically what I want to find. Yes, I want to find the dimension of area. To find the dimension of area, I have to find the dimension of pi r and raised to 2. So now let's first write the unit. So I can say area, the units for area are, pi is unitless, pi is a number, and this is r. So I will say r is measured in meters square. Yes, so the units, so these are the units. This is the unit for my fundamental or my physical quantity area. So now I have this fundamental quantity, right? I have written my physical quantity in terms of fundamental units. And what is that fundamental unit? M. And to represent M, what do we use? To represent M, we use L raised to 1. So basically, what is M? M is L. But now check here. What is power? Power is 2. So this will be L raised to 2. So I can say that the dimension for area is basically L raised to 2. Clear? So dimension for area. So what is the formula? Formula, I'll say pi r square. Right? So this will be equal to, unit will be equal to meter square, and meter square will give me L raised to 2. Correct? Now, so now you will also say that, sir, I chose some other formula. So let's say someone might have used the formula for area as length into breadth, length of a rectangle, right? Length into breadth. So now let's write. So length is measured in meters and breadth is also measured in meters. So units will become meter square. Correct? So dimension for my area is equal to Meter is L and this is raised to 2. So what do you understand by this? You should understand that whatever formula you use, my dimensional formula will come out to be same. It is independent of the formula you use. But you can, so there are many other formulas to use for area, right? Area of a triangle is half base into height. I can also use that and I'll get the same answer. So the dimensional formula is independent of the formula you use, but you should use the correct formula. Okay, you cannot use the formula as, let's say the area of a triangle is b square. Oh, sorry, or you say b cube. Then you're using the wrong formula. Okay, so you have to use the correct formula also. Clear? Now let's move forward. So now what about velocity? So with velocity, what formula do you remember? I remember velocity is equal to displacement upon time, right? So displacement unit is meter, time is second, right? Velocity is equal to displacement upon time. So what is meter? Meter is basically L and second is time. So I will say dimension for meter is L raised to 1, dimension for t second is t raised. So what do I get? L raised to 1 and t raised to minus 1. So this is the dimensional formula for my velocity. Let's find it for work. So what is work? So the formula I remember for work is force into displacement, right? Force into displacement. So what is formula for force? So now for force, I don't know. So now for force, I don't know the unit, right? I know Newton, but I want to write in terms of my fundamental units, right? So for force, I will again break that. Force is basically mass into acceleration into displacement t. Now mass is measured in meters. Mass is measured in kg. I'm really sorry. Mass is measured in kg. Now acceleration measured in meters per second square, and this d, that is displacement, is measured in meters. So what do I have? Kg meter square upon second square. So for kg I have m raised to 1. For meter square I have L raised to 2. And this is 1 upon second square. For 1 upon second square, that will be t raised to minus 2. Right? So the dimensional formula for work is m raised to 1, L raised to 2 and t raised to minus 2. Okay, let's find for energy. So now energy, so any energy, kinetic energy or potential energy. So I know the formula for kinetic energy. Kinetic energy is half m v square, right? Half m v square. So dimensional formula for half is a number and that is a dimensionless quantity. Mass is measured in kg and velocity is measured in meters per second and that is squared. So this will be kg meter square upon second square. So kg is measured raised to m raised to 1. The dimensional formula for kg will be m raised to 1. This is meter square. For meter square I will have L raised to 2. And this is 1 upon second square. 1 upon second square is t raised to minus 2. So the dimensional formula for energy is m L square, m raised to 1, L raised to 2 and t raised to minus 2. That is, m is my base quantity which is raised to the power 1. L is my base quantity which is raised to the power 2. Time, that is t, is my base quantity and it is raised to the power minus 2. So I hope this is clear to you that how to find dimensions. So I will request you now to please solve these fundamental quantities. So let's write for acceleration. So acceleration is basically change in velocity upon change in time. Yes, or I can say acceleration is dv by dt. rate of change of velocity with respect to time. So change in velocity is, so what is change in velocity? I will subtract one velocity from other. Yes, so I will get change. So change in, let's say, some meter, so velocity is measured in meters per second, right? Meters per second, and upon time. So I will upon time. This will be meters per second. So meters per second, meters per second upon time. So time is also seconds. So what do I get? I get meter. Meter is L. This will be L raised to 1. Right? Second square. Second square will be T raised to. Now, this is 1 upon second square. So this will be T raised to minus 2. So I hope it is clear how you can find dimensions for different quantities using the physical, so fundamental 7 fundamental quantities. So I will request you now to please write the dimension for each and every quantity here. Okay, try it by yourself. So please stop the video and please solve them. So these are some more quantities for which you can find. Okay, there will be some quantities for which you don't know the formula or you don't know the meaning of that because you have not covered yet. But as we go on in this course, you will know each and every physical quantity. Okay, so don't worry. If you don't know a physical quantity, please Google it, find the formula and write the dimension for it. So now let's move forward. So now applications of dimensional analysis. Okay, so what is application? So now we learned how to find dimensions of a physical quantity. Now what do I want to do? Now I want to now use the applications, right? I want to apply my dimensional formulas. Okay, so now let's apply. So let's see. So now first application is homogeneity of dimensions in an equation. So now what is this? So now let's see what is homogeneous now. What is homogeneous? Homogeneous means, what do you mean by homogeneous? Something that is, so let's say I make a mixture of salt and water, right? So now what happens? So now if I put salt inside that water, what will happen? The salt will dissolve inside that water, right? Yes. Now if I stir it, what will happen? The particle will be homogeneously distributed in the water. But let's say if I now keep my drink or the salt solution for a while, all the salt will settle down. Yes. So now, so what is homogeneous? Let's say I take this part, this area, and I take this small area. Okay, I divide this into 4 parts. Let's say there are 1, 2, 3, 4 people standing in this area, 4 people standing in this area, 4 people standing in this area, and 4 people standing in this area. Then in this case, I will say that it is homogeneous distributed. That at each and every point, I have 4 people standing in each quarter of the circle. But let's say if this area, all the people are standing here and very few people are standing here, that is in the scattered case. It is non-homogeneous. So now what do we have to do here with this? Let's see. So let's say I go to a shopkeeper. Okay, I go to a shopkeeper and I ask him that please give me 4 kg rice. I ask him that please give me 4 kg rice. And he measures the 4 kg rice using a being balance, and then he throws the rice at a speed of 2 meters per second and gives it to me. He measures the 4 kg rice and he throws the packet at me at a speed of 2 meters per second. So now, will this become 6 kgs? Will this rice become 6 kg? Your answer will be no, right? The rice will remain 4 kg. But 4 plus 2 should become 6, right? So what is the problem here? The problem here is that this unit is meters per second, this is kg. So if this meter per second would have been kg, then in that case I could have written 4 plus 2 kg is 6 kg. But this is not kg, right? This is meters per second. So your argument will be, why I cannot do this? I can, because the units are different. So units are different, right? So this is what we mean by homogeneity of a dimensional equation. So now this means that I can only add two physical quantities of same units. Okay, add or subtract. Okay, add or subtract. I can only add or subtract two physical quantities of same units, and the result will also have same units. So what is this last statement? That if I add 4 kg plus 2 kg, I will get 6 kg. The result will also have the same unit. Yes. So this is what you mean by homogeneity of dimension in an equation. So let's solve using some questions. Okay, let's solve some questions. So first, so if force is given by F is equal to AT plus BT square, where T is the time, what are the dimensions of A and B? So here I can see that AT plus BT square. So dimension of, I can say, and this is force, right? So force is equal to AT plus BT square. So I'm adding these two quantities, so these two quantities should have same units, and this should also have same units as force. So I will say that the dimension of force, if the units are same, the dimensions are also same. So I can say that the dimension of force is equal to dimension of AT, and that should be equal to dimension of BT square. So this will become dimension of force is equal to dimension of A into dimension of T is equal to dimension of B into dimension of T square. Now let's write. So what is the dimension of force? So if you remember, the dimension of force is m raised to 1, L raised to 1 and T raised to minus 2. Those of you who don't know how to write the dimension of force, let's find it here. So I can say that the force is basically mass into acceleration, right? So this will become, mass is basically kg and acceleration is meter per second square. So this is, kg is m raised to 1, meter is L raised to 1, and this is T raised to 2. So from here I will get m raised to 1, L raised to 1 and T raised to minus 2. Should be equal to dimension of A, and T is time, so this is T raised to 1 is equal to dimension of B into, this will become T raised to 2. Now let's solve them. So if I solve them, what do I get? I get m raised to 1, L raised to 1, T raised to minus 2 is equal to dimension of A into T raised to 1. Yes, so if I solve this, I'll get dimension of A is equal to m raised to 1, L raised to 1 and T raised to minus 3. T raised to minus 3. Similarly, dimension for B. To find the dimension for B, what should we do? We should equate my first term and the last term. So if you solve, the dimension of B comes out to be, I am writing it directly, it will come out to be m raised to 1, L raised to 1 and t raised to minus 4. T raised to minus 4. You please try to solve it. So what do you get from here? So dimension of A is mlt minus 3, mlt minus 3, mlt minus 3. So this is gone and this is gone. And for dimension of B, dimension is mlt raised to minus 4. So this is gone, this is gone, and this is gone. So correct answer is option 2. Correct answer is option 2. So this is how you use principle of homogeneity to find dimensions of unknown quantities. Clear? I hope this is clear to you. Let's solve one more question. So the equation of some gas can be expressed as P plus A by V square into, so let's write the formula first. So this is P plus A by V square into V minus B is equal to RT. So now if you see here, this P is added by A by V square, V is subtracted from B. So from here I can say that the dimension of V should be equal to dimension of B, and dimension of P should be equal to dimension of A by V square. Yes. So now here what is this P? So P is the pressure. P is the pressure, it is given in the question, and V is the volume. So now what is pressure? So for pressure I will write pressure is force upon area. Right? Force upon area is equal to, I can say, dimension of A upon volume square. Yes. From here what can I say? I can say that dimension of force upon dimension of area is equal to dimension of A upon dimension of V square. Correct? So dimension of A will be equal to dimension of force, dimension of V square upon area, dimension of area. Now this V is not velocity, this is volume. So from here I will get dimension of A is equal to, now what is dimension of force? Dimension of force is mlt minus 2. So m raised to 1, L raised to 1 and T raised to minus 2 into volume. Volume is L cube, and L cube, and this is square. So this will become L raised to 6 upon area. Area is basically L raised to 2. So now what do I get here? I get m raised to 1, L raised to 5 and T raised to minus 2 and T raised to minus 2. So I hope this is clear to you. Please look at the calculation. So which option should be correct? So if you look, option 1 is matching with my answer. Option 1 is matching with my answer. Okay. So I hope this is clear to you, that how you can use the principle of homogeneity to find the dimensions of unknown physical quantities. Now what if I multiply P plus A by V square with V minus B? So should the dimension of this quantity and this quantity to be same? Not necessary, right? Because I am multiplying force as mass into acceleration, right? Mass and acceleration don't have same dimension. So it is not necessary for that. Let's move forward. So this is a homework question for you. Please do attempt it. This is a homework question. Now let's move forward. Now conversion of one system to another. Okay. So now the second application is conversions of units, right? So the three type of units, different units we studied, right? CGS, MKS, right? And pound system, right? So how to convert one physical quantity in one unit system to another physical quantity? So now you might have heard that I want to convert my kilometers to meters, right? Hours to seconds, meters per second to kilometers per hour, right? So all this conversions we can do using this application. So let's look. So now what is this? So now I know that any physical quantity, so let's say some physical quantity Q, right? Any physical quantity Q has a numerical value, has a number, and has a unit. Yes, any physical quantity has a numerical value and has a unit. So any physical quantity has a numerical value and a unit. So now this is system 1. This is my system 1. And in system 1, I am saying that the numerical value is N1 and these are the dimensional formula. This is the dimensional formula. This is my system 2. And in my system 2, this is my quantity. Now the quantity will not change, right? Because if I say that 60 seconds is equal to 1 minute, right? So they both mean the same thing, right? If I say 60 minutes is equal to 1 minute, 60 minutes is equal to 1 hour. If I say this, right, see they both mean the same. Now this is basically Q and this is basically Q, right? This is Q, this is Q. Now what is this? This is basically my N1 and this is the unit 1. This is basically my N2 and this is my unit 2. Okay, so this is my system 1, this is basically system 2. Okay, so now what we do, we just equate them. And we try to solve them. So let's look at an example and try to solve. So I want to convert 36 kilometers per hour to meters per second. So let's say this is my system 1. Let's say this is what? This is system 1. And what is this? This is system 2. So in system 2, what do I have? So let's talk about system 1 first. So in system 1, this is my numerical value and this is the unit. So I have my numerical value and I have my unit, kilometers per hour, right? In my second unit, so this is equal to second system. In second system, I don't have the numerical value n, right? I don't have the numerical value n2, but I have the unit and the unit is meter per second, right? So kilometer per hour, I will write as kilometer upon hour, right? This is basically kilometer upon hour. Kilometer per hour. So now let's try to solve. So I'll say 36. Now, kilometer, what can I write? I can write kilometer as 1000 meters and hour. So 1 hour is basically 60 minutes, right? 60 minutes. So I can say that 1 hour is equal to 60 minutes. And also I can say that this is equal to 60 and this 1 minute is equal to 60 seconds. So this is basically 3600 seconds. Correct? So 1 hour is equal to 3600 seconds. And this is basically my N2 into meters per second. So if you see here closely, the second cancels with the second, this meter cancels with this meter. 0 cancels with the 0, this 0 cancels with the 0. 2 5s are 18, 2 1s are 2 and 2 8s are 16. Right? So what do I get? I get N2 is equal to 36 into 5 upon 18. So this is 18 1s are 18, 18 2s are 36. So I get N2 is equal to 10. Right? So I get this N2 is equal to 10. So now what is the conversion? So the conversion will be 10 meters per second. So I will say 36 kilometers per hour is equal to 10 meters per second. I hope this calculation is clear to you. Let's look at another illustration. So now I want to convert 1 Newton in dynes. So now let's do one thing. So I will write, so this is my system 1, this is my system 2. Right? So what is dyne? Dyne is basically a CGS unit. Newton is basically my MKS system. This is my CGS system. Okay, so I'll write 1 in 2. Now Newton is basically kg meter per second square, right? Kg meter per second square. Mass into acceleration is equal to N2 into second system is, so instead of kg I'll write gram, instead of meter I'll write centimeter, and second remains seconds, right? Because Newton, what is Newton? Force is equal to mass into acceleration. Mass is kg, this is meter per second square. Okay, so this is equal to Newton, right? So in my CGS system, my kg is represented as gram, my meter I'll write as centimeter, and second remains as second. Now let's look here. So I'll say 1 kg is equal to 1000 grams, meter is equal to 100 centimeter upon, I'll get second square is equal to N2 into grams into centimeter upon second square. So the second square cancels with the second square, this centimeter cancels with the centimeter, and this gram cancels with this gram. So what do I have? I have N2 is equal to 1, 2, 3, 4, 5. So 10 raised to power 5. Right? So I can say that 1 Newton is equal to 10 raised to power 5 dynes. This is my final answer. So I request you to please solve this question. Okay, so this question and this question are for your practice. Please try to solve these questions and write the answer in the comment section. So so that I can pin the correct answer so that others can know. Now, this question is also for you. Please try to solve this also. Now, let's move to the last application. So now what do I want to do? I want to derive, okay, now I want to derive relationship between two or more than two physical quantities. So I have a physical quantity 1, I have a physical quantity 2. Now I want to derive a relationship between them. By relationship, what do I mean? I want to derive a formula, right? So let's see. So now here he is saying that if force, so let's say now, so what kind of formula I want to say? So let's say kinetic energy. Kinetic energy, I know the formula is half mv square, right? I know this formula. So what if I don't know this formula? What if I don't know this formula? Right? So let's see. So how can you derive this? Okay, dimensionally. So what is energy? This is kinetic energy. So I know the greater the mass, greater the kinetic energy of the body, right? Because let's say I have a car and I have a train, and both are moving with the same speed. So can you tell me who will have greater energy? Obviously the train, right? So I can say that the kinetic energy is proportional to mass. Greater the mass, greater the kinetic energy. Now let's say two trains are moving with, one is moving with speed 100 meters per second, other is moving at 200 meters per second. Which will have greater kinetic energy? Obviously the train with greater speed. So I can also say that kinetic energy is also proportional to velocity, right? So this is by intuition or by logic we can say this. Now if I want to derive a formula between them, I will say that the kinetic energy, right? So the dimension of kinetic energy is basically, I will say m raised to something, mass raised to something, let's say x, and v raised to y. I am just equating the dimensions. Now, so what is dimension for kinetic energy? So dimension for kinetic energy is, if you remember, m raised to 1, L raised to 2, and t raised to minus 2. Now this is mass. So mass is basically kg and kg is capital M. So m raised to x, and this is velocity. Velocity is L t minus 1 raised to y. So what do I have? I have m raised to 1, L raised to 2 and t raised to minus 2. This will give me m raised to x, L raised to y and t raised to minus y. So now if I equate here, what do I get? I get, if I equate, so m raised to 1 and m raised to x. So I can say x is equal to 1. This is L raised to 2 or L raised to y. So I can say y equals to 2. From here I can say t raised to minus 2 and t raised to minus y. I can say y equals to minus 2. So now what I am able to achieve? I know that now m raised to 1 and v raised to 2. Yes. So this intuition, from this intuition I can derive this formula. But I cannot derive this 1 by 2, right? I cannot derive this 1 by 2 because 1 by 2 has no dimension. So now we can only check that if my formula is correct or not, dimensionally correct or not, right? So this is what we are going to do. Okay. See, this number I cannot derive. Okay, this can be 1 by 3, 1 by 4, I don't know. But I know that what is the power raised to x, to my fundamental quantity, what is the power, right? Let's move forward. So please let's solve this question first. So now if momentum, area and time are taken to be the fundamental quantities, then the dimension formula for energy. Now, here it is given that my momentum is my fundamental quantity, area is my fundamental quantity and time is my fundamental quantity. So now they have changed the fundamental quantities here. So I want to find the dimensional formula for energy. So we'll again do the same thing, that energy is momentum raised to some x, area raised to some y and time raised to some z. So now what is the dimensional formula for area, for energy? Energy is m raised to 1, L raised to minus 2, L raised to 2 and t raised to minus 2. L raised to 2 and t raised to minus 2. So this will give me, now what is momentum? Momentum is mass into velocity. So mass I can write m and velocity I can write Lt minus 1 raised to x. Area is L square raised to y and this is time raised to z. So what do I have here? I have m raised to x, now L raised to x, t raised to minus x, L raised to 2y, t raised to z. Now I can write m raised to x. Now let's collect all the terms for L. So L raised to x and L raised to 2y. So I can write x plus 2y because powers add. And for t, time, I can say minus x plus z. And this is equal to m raised to 1, L raised to 2 and t raised to minus 2. Now let's compare both the sides. So from here I will say that x is equal to 1. X is equal to 1. Second thing I can say that 2 is equal to x plus 2y. X plus 2y. So from here I will say that, what will I say? That y is equal to, what is y? Y is equal to 1 by 2. Y is equal to 1 by 2. And what about z? So I can say minus 2 t raised to, that is minus 2, is equal to minus x plus z. So z is equal to -2 plus x, and x is equal to 1. So I'll get -1. So z is equal to -1. So now what do I have? So if I check here, my final answer is energy is equal to P raised to 1 a raised to 1 by 2 and t raised to z, and z is equal to -1. So which answer should be correct? P raised to 1, a raised to 1 by 2 and t raised to -1. So third option is correct. So this is how we use dimensional analysis, okay, to find my physical quantity, dimension of physical quantity in terms of some other physical quantity. Okay, so I request you to please solve this question. This is a practice question for you. Please solve it. Okay, also please solve this. Now let's come to the limitations part. So now there are some limitations which we cannot do. So one limitation which we saw was that when I derive the formula, right, this 1 by 2 I was not able to find. Yes, this 1 by 2 I was not able to find. Now if dimensions are given, the physical quantities may not be unique for everyone, right? So let's say for energy and work, as we see here, so look here, for work and energy I have the same dimensional formula. Yes, so I cannot say that what is work and what is energy, right? So this is a drawback, one of the limitations which I have. Second is numerical constants cannot be reduced, right? I cannot reduce the numerical constant as we saw there. I don't know that what is that, a half, is that a 1 by 3, or is there any number or no? So I cannot do that. The method for dimension cannot be used to derive relation other than the product of power functions, right? So only the product of power functions I can use, other than that I cannot use. Fourth is the method of dimension cannot be applied to derive a formula, right? I cannot derive the formula, only I can derive the power raised to it. I cannot know the exact formula. And the last is, even if a physical quantity depends on 3 physical quantities, out of which 2 have the same dimensions, the formula cannot be derived, right? Again the same thing. If in a formula I have energy and work both, then I will get confused that for what I have to, which formula I have to use. Okay, so these are some limitations which you should know. The main limitations is I cannot find the numerical constant. So let's solve this question. The method of dimensional analysis cannot validate exact relationship between physical quantities in any equation. It does not distinguish between the physical quantities having same dimensions. Okay, so now what should be the answer? Yes, the method of dimensional analysis cannot validate exact relationship between, right? It cannot validate the exact relationship. This is true. Now second thing, it does not distinguish between the physical quantities having same dimensions. Yes, if I have two quantities of same dimension, I cannot distinguish between them. So this is also true. Now which option should be correct? So is assertion to this true? Yes, and the reason is also true. Correct? But is it the correct explanation? Okay, is this the correct explanation? So yes, correct. So the answer for this should be my option 1. Correct? Answer should be option 1. So I hope this is clear to you. So I request now you to please solve. How many questions do we have? 1, 2, 3, 1, 2, 1, 2, 3, 4. So I have 6 questions, right? I have total 6 questions. 1, 2, 3, 4, 5, 6. 6 questions for homework. Please solve them. Thank you for joining. If you enjoyed the lecture, please give a like and subscribe to the channel. Thank you for watching. We'll meet in the next lecture. Thank you everyone. And if you have any doubts, please write in the comment section so that I can help you with that.